Shall we start? So welcome to the competition. It's my great pleasure to introduce Velichka Milousheva. So she is from the Institute of Informatics, Bulgarian. Yeah, so
thank you. Dear colleagues, before starting with my talk, I would like to say that it's really a very great pleasure for me to be here in Miami, to enjoy the nice weather in Miami, the sun, and to speak in front of you. I see many friends here from my previous coming to Miami, and it's a pleasure really to be again here. So my talk is divided into two parts. In the first part, I will speak about the minimal Lorentz surfaces in pseudo-Euclidean force space with neutral metric and how we can describe this class of surfaces in terms of invariant functions and a system of partial differential equation. And in the second part, I will speak about the Weierstrass representations, which allow us to find the solutions of this system of partial differential equations. You know that the study of minimal surfaces is one of the main topics in classical differential geometry, which goes back to the 18th century. And Lagrange was the first who initiated the study of these surfaces and found the minimal surface equation when he was looking for necessary conditions to minimize the area functional. So he found this equation which describes the minimal surfaces if they're parametrized as a graph like this. They satisfy this for a differential equation, which is known as the Lagrange equation. And actually, the first non-trivial examples were the catenoid found by Euler in 1744 and the heliquid found by Meunier in 1776. Everybody knows that the catenoid is the only minimal surface of revolution and the heliquid is the only minimal surface built up of straight lines. What is interesting for these surfaces that they're related through the Bonnet transformation, which means that they can be obtained from each other by an isometric transformation. Here I just put the picture to the two surfaces I'm speaking about, the catenoid and the heliquid. Actually, Meunier in 1776 made the link between the curvature and the minimal surfaces, proving that the Lagrange equation actually implies that the mean curvature is zero everywhere on a minimal surface. So the minimal surfaces can be defined in different ways. They are usually defined as surfaces with zero mean curvature, but they can also be characterized as surfaces of minimal surface area for given boundary conditions, or as a critical point of the area functional, or as a graph of the solution of this differential equation. And in fact, this variational definition that the minimal surfaces are critical points of the area functional makes the minimal surfaces the two-dimensional analog of the geodesics, because the geodesics are the critical points of the length functional. So this is some kind of history. And I will mention the Weierstrass representation formula, which describes the minimal surfaces in terms of two functions f and z by this formula. Here f and g, I'm sorry. F and g are two homomorphic functions. So throughout the 19th century, great mathematicians such as Gauss and Weierstrass devoted much of their studies to these surfaces. But also in the last 2 centuries, many other mathematicians studied minimal surfaces in real space forms. And in the last years, great attention is paid to Lorentz surfaces in pseudo-Euclidean spaces with different signature, since the pseudo-Riemannian geometry has many important connections with physics and application in physics. And here I put one theorem of Banqian-Chen from 2011, which gives the classification of minimal Lorentz surfaces in pseudo-Euclidean space EMS for arbitrary M and S. And this classification states that a Lorentz surface in this pseudo-Euclidean M space is minimal if and only if the surface is parametrized in the following way. Beta of u plus theta of v, where beta and theta are two null curves satisfying this condition. And now, our aim is to characterize the minimal Lorentz surfaces in terms of a pair of smooth functions which satisfy a system of two natural partial differential equations. And this actually solves the problem of Wundt-Regge for minimal surfaces in four-dimensional spaces. And this aim is motivated by similar results concerning minimal surfaces in the four-dimensional Euclidean space E4, and also space-like and time-like surfaces with zero mean curvature in the Minkowski space E41. So we are going to study minimal Lorentz surfaces in E42, pseudo-Euclidean space with neutral metric, plus, plus, minus, minus. And our study is based on the introduction of special parameters, which we call canonical parameters. Let me first mention some things about the minimal surfaces in the Euclidean 4 space. Actually, each surface in E4 satisfies the following Wing inequality. Here, K is the Gaussian curvature, kappa is the mean curvature, the normal curvature, I'm sorry, and H is the normal mean curvature vector, I'm sorry. So these three main invariants satisfy this Wingen inequality, and the surface is called Wingen ideal surface if it satisfies the equality case of this inequality identically. And since a surface is minimal if this H is equal to 0, then we obtain that the Gauss curvature K and the curvature of the normal connection kappa of any minimal surface satisfy this inequality. And this inequality actually divides the minimal surfaces into two basic classes. The first class is the class of minimal Wingen ideal surfaces, in which we have the equality case. And the second class is the class of minimal surfaces, I call them of general type, in which k squared minus kappa squared is greater than 0. The minimal Wingen ideal surfaces are also characterized by a circular ellipse of normal curvature. So here I recall the notion. The ellipse of normal curvature at a given point is the ellipse in the normal space, which is defined here, sigma of xx. Here sigma is the second fundamental tensor. And it can easily be checked that if we have two vectors x and y orthonormal base, I'm not very successful with this pointer, so I will not use a pointer. If we have an orthonormal base xy in the tangent space, then for each tangent vector v, we have this expression of sigma vv, which shows that when v goes once around a circle in the tangent plane, sigma vv goes twice around an ellipse, and this ellipse is centered at h, and these two vectors here are the conjugate directions of the ellipse. On the other hand, the surfaces whose ellipse of normal curvature is a circle are also known as superconformal surfaces. And hence, the class of minimal Wingen ideal surfaces coincides with the class of minimal superconformal surfaces. And now we can apply the result of Eisenhardt, which states that the class of minimal superconformal surfaces in E4 is locally equivalent to the class of homomorphic curves. So the first class, in which k squared minus kappa squared is equal to 0, is described as homomorphic curves. About the non-trivial class, the general class, we have this theorem of Tribuzian-Guadalupe from 1985, which states that the Gauss curvature K and the curvature of the normal connection of any minimal non-superconformal surface parameterized by special isothermal parameters satisfy this system of partial differential equations given on the slide, where delta is the Laplace operator. And conversely, any solution K kappa to this system determines a unique, of course, up to a motion in E4, minimal non-superconformal surface with Gauss curvature K and normal curvature kappa. So the minimal surfaces in E4 are described in terms of these two special invariants K kappa by these two partial differential equations. This is the problem solved in E4. Now similar results hold for surfaces with zero mean curvature in the Minkowski-4 space, E41. The class of space-like surfaces with zero mean curvature in the Minkowski-4 space is described by a similar system of partial differential equation, which you can see now. And conversely, any solution to this system determines a unique up to a motion in the Minkowski space, space-like surface with zero mean curvature. Similar result is true from time-like surfaces with zero mean curvature. This is a result of Georgi Ganchev and me in 2013. And we described the time-like surfaces with zero mean curvature by a similar system of partial differential equations for the main invariants K and kappa. Here, instead of the standard Laplace operator, we have this hyperbolic Laplace operator, delta H. Here we use a special so-called canonical parametrization of the surface. And let me note that in the Minkowski-4 space, there is not the analog of superconformal surfaces, since we have both for the space-like case here and for the time-like case here, we have the expression kappa squared plus k squared, which is always greater than 0. Of course, we exclude the case in which both k and kappa are equal to 0, because in this case, the surface lies in a two-dimensional space. And let's go further to the pseudo-Euclidean space with neutral metric, E42. The space-like case, space-like surfaces with zero mean curvature, also called maximal space-like surfaces, are characterized by Sakaki in 2002. And we have a similar system of partial differential equations for the main invariants, the Gauss curvature and the normal curvature. And here we have that all space-like surfaces with zero mean curvature satisfy this condition. K squared minus kappa squared is greater or equal to 0. So in the four-dimensional pseudo-Euclidean space with neutral metric, we again have the analog of superconformal minimal surfaces. And they are characterized again as having circle as an ellipse of normal curvature. And now we focus our attention on the minimal Lorentz surfaces, so time-like minimal surfaces in E42. And they can be divided actually into three basic classes. So that was the object we are working on, minimal Lorentz surfaces. Here we have three basic classes. In the first one, we have k squared minus kappa squared is greater than 0. In the second class, the surfaces are characterized by equality. And in third class, k squared minus kappa squared is less than 0. And I would like to pay attention to the third case, because such a case exists only in the pseudo-Euclidean 4 space, E42, with neutral metric. Such a case does not exist neither in the Euclidean force space nor in the Minkowski force space, nor for a space-like minimal surfaces in the pseudo-Euclidean space with neutral metric, only here. The class of minimal Lorentz surfaces, which satisfy the equality case, that is the second class, is characterized analogously to the minimal superconformal surfaces, but in the Euclidean space. But instead of ellipse of curvature, here we have to consider the so-called hyperbola curvature, the hyperbola of normal curvature. It is defined by Bayard, Patti, and Sanchez-Bringas. And the minimal Lorentz superconformal surfaces are characterized by a rectangular hyperbola. And so we focus our attention on the general case. The general case we have locally, of course, because we studied the local theory. In some subdomain, k squared minus kappa squared is greater than 0 or less than 0 in the whole subdomain. And first, we consider the case when the first normal space is one-dimensional. The first normal space is the subspace of the normal space, defined as the image of sigma p. Sigma is the second fundamental form. This is the space spanned by all sigma of xy, xy run in the tangent space. So we have this theorem too, which describes the minimal Lorentz surfaces whose first normal space is one-dimensional, and the theorem states that such a surface is either a degenerate hyperplane, a flat umbilical surface, or a quasi-umbilical surface, all lies in a non-degenerate hyperplane. So the main case we have to consider is the case of minimal Lorentz surfaces of general type whose first normal space is two-dimensional. And for this class of surfaces, we introduce special parameters, which we call later canonical parameters, and find a geometrically determined moving frame field, x, y, n1, n2, which is determined by the canonical directions. X and y are tangent vector fields, collinear with the two canonical directions, n1 and n2 are normal vector fields, again determined by the canonical directions. With respect to this geometric frame field, we have the following Frenet type derivative formulas, which you see on the screen. And these derivative formulas are expressed by smooth functions mu, nu, gamma 1, gamma 2, beta 1, and beta 2, 6 smooth functions. Actually, these functions, when reparametrized by canonical parameters, are reduced to 2. And that's the idea of solving the Montareggi problem for this class of surfaces, to reduce the number of functions and the number of equations that determine the surface up to a motion. And this is the fundamental existence and uniqueness theorem for this class of surfaces. It is a result with my PhD student, Yana Alexieva, in Journal of Geometry and Physics. The theorem states that if we are given two smooth functions, mu and nu, defined in some domain D, and satisfying the conditions which are given here, actually we have two differential equations and these conditions of non-triviality on the first line. And if we are given an orthonormal frame at a fixed point P0 here, such that the first vector is space-wide, the second one is time-wide, and the first normal vector, the sign is epsilon equal to plus or minus 1, the other one is respectively minus epsilon, then there exists a subdomain D0 and the unique minimal Lorentz surface of general type, which passes through this given initial point. And these two functions, mu and nu, are the geometric functions of the surface. The case epsilon equal to 1 corresponds to the first geometric normal vector to be space-like, and the k is equal to epsilon -1 corresponds to a time-like vector n1. So in this case, the Laplacian is the hyperbolic Laplacian. Hyperbolic, yes, yes. What I mean here, delta H. In this case, delta H is like this minus. So the meaning of this theorem is that any minimal Lorentz surface of general type is determined up to a rigid motion in E for 2 by two invariant functions, mu and nu, satisfying the system of two natural partial differential equations. And we call this system of natural partial differential equations the background system, describing this class of surfaces, the minimal Lorentz surfaces in E for 2. The idea here is that the functions mu and nu are parameterized by special parameters canonical, and that these parameters give us the possibility to minimize the number of functions and the number of equations which describe this class of surfaces. Now, this is reduced to 2 in this case. And if we, in terms of these canonical parameters, everything can be calculated more easily. Here, what you see is the connection between these two functions, mu and nu. They have some geometric interpretation, and it is in fact hidden in these formulas expressing the Gauss curvature K and the normal curvature in terms of these canonical isothermal parameters. So in terms of the invariants K and kappa, the theorem looks as follows. And it is similar to the other cases which were studied before. So we have this, actually, this is the background system of partial differential equations describing this class of surfaces. Any solution to this system determines a unique minimal Lorentz surface of general type with Gauss curvature K and normal curvature kappa, and the parameterization is canonical. If we have a solution of this equation, these parameters of K and kappa are the canonical parameters of the surface. And now, it is interesting to answer the other question. How can we find explicit solutions to this system of two partial differential equations? And to find the explicit solutions, we use the Weierstrass type representation formulas. This problem is solved for surface minimal surfaces in E4 and space-like minimal surfaces in E41 and E42 by Georgi Ganchev and Krasimir Kanchev, and they use special kind of Weierstrass representation which allow to solve the problem. For space-like case, they use complex numbers, and here for the Lorentz or time-like case, we work with the algebra of double numbers or paracomplex numbers, which is the hyperbolic analog of the algebra of complex numbers. So I come to the second part of the talk, which concerns Weierstrass representations of minimal Lorentz surfaces in E42.
So in this previous discussion, I mean, how difficult is the generalized using to Riemannian local?
What we are interested in here is the local theory of two-dimensional surfaces in pseudo-Euclidean four-dimensional space with neutral metric. And we have this Bonnet type theorem of existence and uniqueness theorem, which in case of surfaces can we state it in terms of functions. Because in the general case for submanifolds, this theorem, the general existence and uniqueness theorem is stated in terms of vector bundles and connections with vector bundles. So here we study surfaces because we want to describe in terms of a minimum number of functions, invariant functions.
But I mean, for global case, two sections,
we can make some connection, yes. We can connect this surface, this theory. Okay.
This aspect holds, for instance, if you try to look to two surfaces, but inside a non-flat space with some semi-Riemannian metric, like you are not more on the.
Yes, you mean you are not more in a flat embedding space.
Yes.
It's an interesting question, but we haven't studied yet. The problem of Wundt-Reg to minimize the number of invariants describing the submanifold. We haven't studied. So now about the Weierstrass representation. Our aim is to find canonical Weierstrass representation, which will help us give explicit solution to the system of partial differential equations, to make the connection with the partial differential equations. So we start with surface M, parameterized locally by isothermal parameters, because they are the most natural parameters in this case, which means that the coefficients of the first fundamental form satisfy this condition. E is equals to minus G, and F is equal to 0. And as a consequence of Chen's theorem, which I showed you at the beginning, we can formulate this proposition. Let beta and theta be two null curves satisfying this inequality. And then the surface psi, parameterized as the sum beta of u plus v plus theta u minus v, gives a minimal Lorentz surface parameterized by isothermal parameters. This follows from the theorem of Bankian-Chen. And conversely, any minimal Lorentz surface in the pseudo-Euclidean force space with neutral metric can be parameterized locally in this way. So we start from here. And we consider a null curve beta in E for 2. This is a null curve, which means that this condition holds for the first derivatives. And first we prove some kind of Weierstrass representation of the null curves. This is proposition 2, which states that each null curve beta can be parameterized locally in such a way that either first or second case holds. The first case, beta prime, is determined by one function f and this vector, which is constant vector. Here epsilon, epsilon 3 and epsilon 2, epsilon 3 are plus or minus 1, and we have one for smooth function f. This is the trivial case, or in the non-trivial case in which the null curve is non-degenerate, we present the curve in terms of three smooth functions, f, g, and h, by the following parameterization here. We have function f in front here, and then the four coordinate functions of the curve expressed in terms of g and h. So we obtained from the Chen's theorem and this proposition, we obtained the Weierstrass representation in isothermal parameters of any minimal Lorentz surface of general type. The theorem states that up to change of the parameters, any minimal Lorentz surface of general type has locally this Weierstrass type representation here in isothermal parameters, where beta and theta are null curves satisfying these equalities for beta prime and theta prime, which means that we express the surface in terms of 6 functions, f1, f2, g1, g2, h1, and h2. And after that, our aim is to find special parameters, which will simplify and reduce the number of functions. Here I change the notations instead of beta and theta for simplicity on this slide, and furthermore I use alpha 1 and alpha 2. So we have that each minimal Lorentz surface in E42 corresponds to a pair of null curves alpha 1 and alpha 2 satisfying this condition. And conversely, any such pair of curves generates a minimal Lorentz surface parameterized by isothermal parameters in this way. Here, the null curves alpha 1 and alpha 2 are determined up to numeration, up to reparametrization and translation. That pair of null curves, which corresponds to a minimal Lorentz surface. And now, how we will define the canonical parameters? First, we consider the so-called natural parameter of the null curve. If alpha is a non-degenerate null curve, it is said to be parameterized by natural parameter holds for the second derivative of alpha. This natural parameter is sometimes called pseudo-arc parameter because it is analogous to the arc parameter in the case of non-null curves. So in addition to the isothermal parameters, we can consider also isotropic parameters. Here they are denoted by T1, T2. And they are connected with the isothermal ones by these formulas. So in terms of isotropic parameters, we have this parametrization of the surface. And here are the definitions of canonical isotropic and canonical isothermal parameters. If M is a minimal Lorentz surface of general type with isotropic parameters T1, T2, we said that they are canonical if T1 and T2 are the natural parameters of the corresponding null curves, alpha 1 and alpha 2. And if we consider minimal surface parameterized by isothermal coordinates UV, then we say that UV are canonical if the corresponding isotropic coordinates are canonical. So the canonical coordinates of a given minimal Lorentz surface are determined up to numeration, sign, and an additive constant, because if T and S are natural parameters of one and the same null curve, we have this relation. Here C is a constant. And now, having the canonical parameterization, we obtain this theorem, which is denoted here by 6. It is a joint result with Ognyan-Kasabov, published in Journal of Mathematical Analysis and Applications. And this is the canonical Weierstrass representation of the minimal surfaces, Lorentz surfaces. If M is a minimal Lorentz surface of general type, parameterized by canonical isotropic coordinates, then M has the following canonical Weierstrass representation, given here by number 2, where G1, G2, H1, H2 are smooth functions satisfying some conditions here for non-degeneracy of the curves. And conversely, if we are given two pairs of smooth real functions satisfying these conditions 3, then there exists a minimal Lorentz surface of general type, which is parameterized by canonical isotropic coordinates and have this Weierstrass representation too. Here I would like to say that actually there are many Weierstrass type formulas characterizing space-like or time-like surfaces in three-dimensional Lorentz space. For example, here I listed some of the results of Dushan and Magid in 2013, Sintra and Tonis 2018, Lira, Melo and Mercuri 2018, 11 of B. Shipman, P. Shipman, and Packard in 2017. And there are also others which are not listed here. They concern space-wide or time-wide surfaces in three-dimensional Lorentz space. And they are connected with some Weierstrass type formulas. And here is one result of Victor Paty in 2016. In which he gave a Weierstrass representation of minimal Lorentz surfaces using spinors and Lorentz numbers. Lorentz numbers are also called double numbers, as I mentioned before, hyperbolic numbers, paracomplex, split complex, many terminology is used for this. And what I would like to say is that all these known Weierstrass formulas express everything in terms of homomorphic and anti-homomorphic functions. So our approach here gives this advantage that the surface and all its invariants are expressed in terms of real valued functions. So the Gauss curvature K and the normal curvature kappa, in terms of the canonical parameters, are expressed by these formulas denoted by 4 here in terms of 4 real valued functions, G1, G2, H1, and H2. And actually, in such a way, we can solve explicitly the system of partial differential equations, which was our aim. So we have this theorem. If K and kappa is a pair of functions, which is a solution to this system of partial differential equations, which looks very complicated, then the solution is expressed in this way in terms of 4 real functions of one variable, satisfying the inequality conditions about the degenerance. And conversely, each such quadrupole of real functions of one variables generates, according to these formulas, a solution to this system of partial differential equations. And of course, we can ask how 2 pairs of such functions are describing one on the same surfaces correspond. So this is solved in this theorem. 2 different quadrupoles of functions can generate one on the same solution, of course. And they are connected by these linear fractional transformations of this type here.
These are modulus transformations, right?
Mm-hmm. Yeah. We just give the connection between, if we want to obtain one on the same solution, one on the same surface, we have to keep in mind that all generating functions are connected by these formulas. The condition 3. Mm-hmm. This condition 3 actually excludes degenerate surfaces, null curves. Yeah, I mean the null curves that corresponds to the surface. And so our aim was to find a system of partial differential equations describing this class of surfaces, minimal Lorentz surfaces, and to show how we can solve explicitly this system of surfaces. And actually, we describe everything in terms of 4 functions. So we can easily now construct the minimal Lorentz surfaces in the pseudo-Euclidean 4 space with neutral metric. And here you can see one example. In this example, we take G1, H1, G2, H2 to be defined in this way in terms of T and S. And if we consider the null curves alpha 1 and alpha 2, whose derivatives are given by these formulas, then after integration up to constant vectors, these null curves are parametrized in this way. And then we construct the corresponding minimal Lorentz surface using the canonical Weierstrass representation formula. We obtain a surface parameterized here in this way, first, second, third, and last coordinate functions. These are the coordinate functions of the surface. And to have the condition for non-degeneracy, we have to assume that in this case, V is different from plus or minus 1/2. Actually, more important is to calculate the Gauss curvature and the normal curvature for this example. And you see here the expressions. We obtain actually a solution to the system of natural partial differential equations. In this example, things are easier because we express K and kappa are expressed in terms only of one variable. But in the second example, you will see another example. Again, we define G1, H1, G2, H2 in this way. Calculate the null curves alpha 1 and alpha 2 generated by these four functions, and then apply the Weierstrass, canonical Weierstrass representation formula and obtain this surface. And the Gauss curvature and the normal curvature of this surface look like this. More complicated. They depend on both parameters U and V, and these two functions give a solution to the system of natural partial differential equations. That was, in short, the theory. There are many calculations hidden here, which I just skip, and I just mentioned that we use the algebra of paracomplex numbers. Here I gave some references if somebody is interested. And thank you for your attention.